shake, that means...
Okay, so a light year is a distance. A lot of people get confused. Light year is a distance. It is the distance light travels in 1 year. Because light travels very, very far. With this speed, you can imagine it's very quick. It takes about 8 minutes for light to get from the Earth to the Sun, or vice versa, the Sun to the Earth. And the nearest star to us is 4 light years away. That's Alpha Centauri. Not the Sun. The Sun is a star too. But yes. The nearest star that is not the Sun is Alpha Centauri.
How many light years?
4. So Zach, if Alpha Centauri is 4 light years away, how long does it take for light to reach us from Alpha Centauri?
12 billion.
No, not quite.
4 years?
Thank you. 4 years.
Light years.
Okay. So when you see Alpha Centauri in the sky, you're not actually seeing Alpha Centauri. You are seeing Alpha Centauri 4 years ago.
That's pretty cool.
How many years did you say?
Okay, come on, guys. Hold on. So
You know, it's just that smart.
now, just like sound waves are created by vibrating objects, light waves are created by vibrating electrons. Electron is a charged particle. Anybody remember what the charge of an electron is? Positive or negative?
Positive.
Taylor. Guys, Taylor P., what do you think? It's not positive?
Listen to me.
So it is negative. Good. So it's negative. Electron is a negative charge. As it vibrates, it creates these light waves, the electromagnetic waves. Okay. So, electromagnetic waves are broken up into what we call the electromagnetic spectrum. The electromagnetic spectrum consists of all the different electromagnetic waves at different wavelengths and frequencies. At one end, we have very large wavelengths. At the other end, we have very short wavelengths. What does that mean about their frequencies? Josh, higher or lower frequency? Higher. Long wavelength means lower frequency. Short wavelength means higher frequency. Okay? Now, the electromagnetic spectrum consists of a lot of different waves, most of it which we cannot see. We can only see a very little part right in the middle here called the visible light spectrum. It is just right here, that arrow. Everything else we can't see. This is radio waves, microwaves, and infrared. No. And ultraviolet, X-rays, and gamma rays are shorter wavelength, higher frequency. These are more energy. Less energy on the other side.
So we can see from where to where?
From about there.
Everything.
So from there to...
Yeah, right there. Okay.
Basically, we can only see physics.
Actually, we can see about 10 to the 14th hertz frequency, and that's about it. The visible light spectrum goes from red to purple through orange, yellow, green, blue, indigo,
What about like,
violet. We'll talk about the colors later. Yeah.
some animal that lives at like night, like a bat or an owl?
Some animals have wider or shorter frequencies. Like cats can see further into the ultraviolet than we can. Dogs can see further into the infrared than we can.
So dogs do see color?
Yes, but they don't see all the colors because they don't have the same cones. But that's not biology.
Dogs see in black and white.
Guys, yes, that's not correct.
Dogs see in yellow and blue.
So, The electromagnetic spectrum goes from radio waves at the weakest to gamma rays at the strongest. The waves at the strongest will actually go straight through most objects because they're such high frequency. Okay. Which brings me to the concept of transparent and opaque. A transparent means light will pass through you. Another way to say that is the light hits the object and then gets re-emitted through that object. If it's opaque, the light does not pass through it. Another way to say that is the light waves are absorbed. They get absorbed and not re-emitted. Now, the weird thing about opaqueness and transparency is they're not fundamentally different. The same object can be transparent to some frequencies of light and opaque to others. For example, glass. You can see through glass because visible light moves through it. However, infrared light and ultraviolet cannot move through glass, so it is opaque to infrared and ultraviolet light. It's only transparent to visible light. This happens quite a bit, where some light will pass through and others won't. For example, X-rays will pass through almost anything, but they won't pass through bones. So your bones are opaque to X-rays, but your skin and stuff is transparent to X-rays.
Because of the calcium?
It's because of what they're made of. So you can see this calcium and a variety of other things. I don't know the exact elements that stop it. Okay, UV light, infrared light, normal light goes through. These ones get absorbed. Okay. Now, the big thing you need to understand about light as it travels through materials is it changes speed.
How?
It slows down. Light, when it goes through vacuum in outer space, is the fastest it can ever be. 3 times 10 to the 8th meters per second. But once it starts going through something, it slows down. It has to do with how fast the particles re-emit the light after it hits them. Sometimes it takes very short periods of time for it to re-emit, which will slow it down just a little bit. Sometimes it takes longer, and it slows it down much further. Yes, Zach?
So what happens when you turn on the light and it flickers and it takes a little bit to come on?
That's the filament burning up. It's starting to power. But anyways, so light travels through air a little bit slower than it travels through vacuum, but it's very similar. But when it goes through glass or water, it slows down much lower. But remember, this is a lot like interference, so the change in speed is not permanent. Once it slows down, it speeds back up as soon as it reaches another material. So when it goes through glass, it's fast, slow, fast again. It doesn't keep that permanent change. This change in velocity is important to refraction and reflection, which we'll talk about in a couple chapters. Okay. Shadows. Yes, we all have a shadow. How shadows form is pretty obvious, actually. A shadow forms because light can be thought of as a ray. A ray is a beam of light. And when you have a light source like a light bulb, what you're getting is a whole bunch of rays of light all at once. So it's a bundle of these rays. When an object blocks some rays but other rays go through, the part where no light is getting through is the shadow. So we got a light source here. It hits this object. It creates a shadow because the rays can't get to this part. Because light only moves in straight lines. Only moves in straight lines. It can bend when it goes through a material because it slows down, but it doesn't move in curves.
I have a question.
Yes.
Then what about like those things where you're sitting in and
Guys?
the light goes around you so you can see everything?
It uses mirrors to reflect it around. Okay. Anyways, light can be turned. It can bend when it goes from one material to another. It can be reflected, but it does not move in curves naturally. It moves in straight lines. So we call two different forms of shadow. We call this part the umbra. That's the total shadow. That's where absolutely no light is getting to it. It's called the umbra. Then we have another part. It's the fuzzy part of a shadow. You guys ever see a shadow where it's really dark in parts, but on the edges it's kind of lighter and blurrier? That blurry part's called the penumbra. And what's happening there is it's only blocking some of the light.
You changed that on purpose.
Oh, sorry.
Yep.
Okay. It's only blocking some of the light. So, as you can see here, this wide source, the light from this edge actually gets blocked, but it illuminates this part down here. So, this part's getting half illuminated and half shadowed, so we get a half and half penumbra. This part's getting absolutely no light, so we get the umbra part. What would happen if I pulled this source further back?
The umbra would
Increase.
decrease, and the penumbra would increase.
So if I pulled this light further away from this ball, would the umbra get smaller, larger, or stay the same?
Yeah, I think I agree.
Ruth, what do you think? If I took this light and I moved it further away,
There would be more rays going around the person.
so would the umbra get smaller?
No.
Would it get the same, or would it be larger?
I think the umbra would be small.
The umbra would get smaller, and the penumbras would get larger, because more light would get around it. This is a little bit how eclipses work, where this is the Earth, the moon would be over here, this is the sun. When Earth's shadow falls on it, we get an eclipse. The other way around, when this is the moon and the Earth is over here, and that's the sun, that's a solar
Like a
eclipse.
total eclipse, it's like an umbra. Is that
Yes. Yeah. Okay. So it can happen because there's multiple sources of light. You ever stand on the street or in a room with two lamps going, and your shadow is not nearly as dark when there's more than one lamp on you, right? It's because the other lamp is filling in some of the shadow the first lamp is creating more of a penumbra effect. If there's enough lights, you won't have a shadow at all, because they'll fill up all the penumbras. Okay. Any questions on how shadows form? Okay, polarization. Now, polarization happens because light travels as transverse waves. Light is a transverse wave. I'll move in a second. Light is a transverse wave and not a compression wave, which means it goes up and down like this. Remember, we use slinkies to do this? But each wave is oriented by which direction the electron's vibrating. If the electron's vibrating up and down, the wave is going to be up and down. If the electron's vibrating side to side, the wave's going to be side to side like this. If the electron's at an angle, the wave's at an angle. Now, for most things, for most sources of light, like candles or the sun or whatever, all the electrons are random. They're all moving at different angles, so all the light is what we call non-polarized, which means they're not all the same direction. Some are up and down, some are at an angle, some are left and right. They're all different orientations. The orientation is called the polarization, by the way. So most sources are not polarized because the electrons are just all going at random, moving back and forth at random. Normally we can't tell the difference between a light going up, down, one going side to side, or how it's oriented. Doesn't matter to us. But this polarity can be exploited. With what we call a filter. If you use a polarization filter, it will block all the light that is not at the same angle as the filter. So for example, if you have this filter that is up and down slits, all the side-to-side waves and all the diagonal waves can't get through. Only the up and down waves get through. Like that, yes. The blinds are kind of a horizontal filter. Please don't open it. I can't. The glare is too much. Thank you. Okay. However, when you get a reflection off a surface, like a horizontal surface, like a car, the light tends to get polarized from reflecting off that surface in the same orientation as the object. So, a wet road, for instance. Light reflects off the water on the road. What polarity do you think the waves are going to be coming off? Horizontal, vertical, diagonal, random? Hallie, what do you think? When it hits the wet surface of the road is flat, the water is flat, so it's not going to be vertically, but it's going to be
The last one. Horizontal.
horizontally. Thank you. It's going to be horizontally. So if you use a vertical filter, you'd block that glare. This is actually pretty common in driving glasses. With driving glasses, they have a vertical polarity, so all reflections off horizontal surfaces get blocked. So it really cuts down on glare. This also, anybody go skiing? You ever wear those glasses? The goggles. They're polarized. Guys, they're polarized because snow is flat and the light reflecting off it is horizontal polarity. So the glasses have a vertical polarity, so it blocks the horizontal beams. That's how they work. They do make things darker though, right? It's hard. It's like sunglasses. Well, they're going to make things a little bit darker no matter what. And the reason is you're getting less light. All the diagonal and horizontals aren't getting through. Only the verticals are getting through. Okay? You can actually do 3D using polarity. What you do is you put part of the image horizontal, part of the image vertical, and then have one eyeglass horizontal, one eyeglass vertical, so you only get part of the image. It's like doing the red and blue 3D viewing, but doing it with polarity. Yes?
Why wouldn't we need glasses for like surfing? Like goggles or something?
It helps, but the problem, the waves aren't usually flat, so it's not going to help that much because waves are moving, so they're getting in more of an angles.
Reflection on the water.
If the water was still, then yes, they would very, very much help. Yes?
What you were saying about the 3D being able to see it with
Uh-huh.
two different filters, is that why 3D cameras have two lenses?
Yes, because they film two separate parts of the film. They superimpose them over each other, and then each lens forces you to only see one of them. And your eye is stereoscopic, so if you see two things, your eye will read it as three-dimensional. Yeah. We usually do it with color. One lens is red and one's blue, and then you have a red lens and a blue lens, so you can only see part of the image at a time. It's the same concept with polarity. We're going to work with polarity filters later this week. Because you can do some really cool stuff with them. Any questions on polarization? I want to do one more slide. Okay. This brings us to color. The color spectrum is created because white light, the light that comes from the sun, more or less, is actually made up of all colors. These are all the colors.
No, they aren't.
Well, there are shades between them, but these are the actual distinct colors of light. Red, orange, yellow, green, blue, indigo is a dark blue, violet's purple.
Indigo only gets mentioned like this.
It's important for science because it has a very distinct frequency. And white light is all of them mixed together. And the way you can see that is with a prism. When you put white light through a prism, it splits into a rainbow. What's happening is the light is slowing down, and since you're hitting at an angle, different frequencies slow down more. So red doesn't slow down as much, purple slows down more, so they turn. That splits them up, open.
Green the widest.
It's not, it's just the other colors near it kind of blend in with it. Now, Newton actually did an observance with two prisms. When you use two prisms and you put white light through and then you take that rainbow that you got from the first one and put it back through a prism, you get white light again. You could remix them.
What would happen if you shine, like, if you had, like, lasers, you all pointed them, like, directly towards each other into a prism, would it turn into white light?
The problem is lasers are one frequency, so you can't split it because it's only one color.
Yeah,
And
but
it's-
what if you had all of the colors?
If you had a white light prism laser, I don't know of a white light laser, but if you had all 7 colors,
And then you pointed at one spot, would you get white light?
yes. If you did it right with 7 different lasers, each of different color, and put them through a prism and brought them to a single point, it would be white. Okay, and black, by the way, is an absence of light.
No, it's not. Black's a color.
Guys, in lights, black is not a color; it is the absence of color. So that's how we break up the color spectrum.